All right, so now what we're going to do is we're going to review all of the reactions of alkenes that we have so far. Now here's the thing. I'm not saying this is all you should know, but this is a nice little packaged video, not that little, it's going to take some time, where we're going to go into every reaction that you should know of alkenes so far. There are more important things like the mechanism, intermediates, shifting, all sorts of other stuff that we can talk about, but this is a nice review of all the reactions. So let's go into it. All right, first one, HBr, and I've got this grouped in terms of its mechanism type because that helps to kind of study these together. So HBr plus alkenes, HBr or H2SO4. Anytime we have an acid plus an alkene, we're thinking we're going to get a carbocation intermediate. HBr, HCl, HI, those are all the same. H2SO4, H3PO4, H3O plus, any acid plus alkene, think that's going to give us a carbocation. Whenever we have a carbocation, we have the possibility of shifting that carbocation. So in this case, you would get the carbocation here, but it would shift over to the tertiary position because that's a more stable position. So in the end, where does your bromine add? The bromine adds to the tertiary position, not to the secondary position. Is that a chiral center? It's not. So I'm not going to glue stereochemistry. I'm going to leave it all flat, leave it all planar, and move on. Okay, what about H2SO4 and water? So in this case, again, I have a carbocation. Just making little notes. I'm not going through the entire mechanism here. Because it's a carbocation, I need to check for shifts. Again, not saying every carbocation will shift, but if there's a better position next door, it will shift. So we form the carbocation here. It shifts over to that position. So you end up with an OH on the more substituted side. Okay, those are the first two reactions. Carbocations, we see very similar reaction mechanisms there. What about oxymercuration reduction? So this one, it is a Markovnikov addition, but remember, because it's a bridge, think there is no shifting going on. There's no carbocation here. It doesn't shift over. So yes, it's Markovnikov. It's going to add to the more substituted side, but it's not going to shift like the previous reaction. So it's good to see this right back to back with H2SO4 and water, because in a lot of cases, this will give you the exact same product if there's no possibility of a shift or if it's already on the more stable position. But in some cases like this, you get different products. So here OH adds there. It is still Markovnikov, so you're still adding it to the more substituted side. Think mercury, Mark. Mercury is a Markovnikov reaction. Is that a chiral center? It is, where the OH adds, it could be a wedge, could be a dash, and they are different. Because that's a chiral center, you are creating different stereoisomers here. So this question did specifically say, as most questions do, to consider different stereoisomers and draw them both. What about BH3? This is a different mechanism entirely. This one, remember, we get the boron. The boron is bigger than a hydrogen, so it likes to go on the end of the chain, on the less substituted side. So in the end, you're going to add an OH group to the less substituted side of the double bond. So this one is an anti-Markovnikov addition. The OH goes on the less substituted side. Technically, it's also a syn addition. In a lot of cases, we don't see that just because the H that were added here, that's not a chiral center. And the OH is also not a chiral center. So you don't really see it in a lot of cases. But you should know it is a syn addition of the H and the OH. But again, in something like this, it doesn't make a difference because you can't see what that does. Is that a chiral center? Again, no. So we're not going to draw two different options. What about Br2 with CCl4 versus Br2 with water? So I'm grouping these two together. These are both your bridge intermediates. So Br2 CCl4, remember CCl4 is inert. So CCl4 or maybe CH2Cl2, those things are not reactive. They don't do anything. So inert means ignore. Don't tell anyone that, because that's not, don't tell your professor that, because they're gonna be like, no, it's not unimportant. It is unimportant. We don't really care about it. Br2 CCl4 is the same thing as just Br2 alone. So make your bridge, attack the bridge. We're gonna get anti-addition. So if one bromine is on a wedge, the other bromine must be on a dash. And notice, draw those first, because then you can always remember those are anti. Then go back and worry about the methyl. So the methyl is on the opposite face here on that carbon. The other option, though, is if your bridge was on the other face, so if the bridge was on one face, you still attack from the other, but what if the bridge was on the dash in this case, or on the wedge? Well, in that case, maybe your new bromine comes in on the dash, Your old bromine from the bridge was on a wedge, and again, the methyl is on the other face. Those two are different, draw them both. So how's it different with Br2 and water? Well, the first step is the same. You make the bridge, so this is also a bridge, but the difference is when the water attacks here, you get an OH, as opposed to bromine attacking, you get a Br. So still, anti-addition. OH goes to the more substituted side, Br on the less substituted side, still anti to each other. The methyl still just kind of hanging out, doing its own thing on the other face. Other idea here, other option would be if the bridge was on the other face, you get bromine on a wedge, still OH on the other face, anti-attack, so OH would be on a dash, and then methyl would be on a wedge. Those two are different because this is Markovnikov, because whenever you attack that bridge, it will be on the more substituted side. That's why the OH goes on the more substituted side. Is this one also Markovnikov? Like, yeah, technically, sure, but because they're both bromines, we can't really see that it's Markovnikov. But when it's something other than bromine, yeah, it matters where you attack. You have to attack on the more substituted side. All right. By the way, if you're like, wait a minute, wasn't this one also a bridge? So wouldn't this one also have anti in terms of its stereoselectivity? Technically, yes, but remember, after step 2, no, we lose that stereoselectivity. So in most cases, it won't matter, but you should know that with oxymercuration, there is no stereospecificity. You can get the OH and the H on the same face, opposite faces, both. Okay, next 3 reactions. And these are reactions that we really don't study the mechanism of much. You have to know what they do in terms of predicting the product. OSO4, that is a syn addition. So that's a syn addition of that crazy looking osmium with all the 4 double bonds, all bizarre looking. So here, syn addition of 2 OHs. You're going to add both OHs to the same face. So let's say they both get added to the top face. So you get 2 OHs on wedges. If the 2 OHs get added on the top face, what happens to the methyls? They get pushed down to the bottom on the dash. Okay. What if we add to the other face? What if both OHs add from below? If you can't see in your mind whether that's going to be the same or different, draw them. So draw them, and then ask yourself, is this the same? If it's the same thing, you can draw it, but it helps to see it on paper before you make your decision. Is that the same thing just flipped over? Yes. If I take it and flip it vertically, it's the exact same thing. So you're like, all right, I'm not going to draw both or else you'll lose points. That is not correct to draw both. And again, cross it out much harder than that, but I'm just showing you that to show you like it is still there if you want to look at it, but it's not different, so don't include it. What about O3? So this one was our ozonolysis reaction. We don't really study the mechanism. Ozonolysis, meaning ozone breaks the bond. That's what ozonolysis means, break the bond. So we're going to snap the bond in half. And this one's a little bit tricky because if you have a ring and then you snap one bond in half, you just get a long chain, right? So this carbon over here, like this part of the ring is still intact. So when you have a ring like this, it helps to number. So let me number starting on one side of my double bond, then going to the other side of my double bond. I'm going to break that open and then redraw my big 6 carbon chain. So 1, 2, 3, 4, 5, 6. 1, 2, 3. There we go. One more. I'm going to renumber it. The whole point of numbering is because then the numbering gives you an idea of where things are. On carbon 1, what did we have? We had a methyl and then the double bond. Okay. On carbon 6, what did we have? We had a methyl and a double bond. And then the whole point of this reaction is once you split it open, you're going to add oxygens where the double bonds are. So there we go. We get this long, in this case, diketone. Sometimes you get a ketone and an aldehyde. Sometimes you might get 2 aldehydes. It just depends on what you had attached at those carbons. So numbering, super, super useful tool. Numbering is one of your very few friends in this class. It helps you in a lot of these reactions. H2 platinum or H2 palladium or H2 nickel. It's H2 with some metal catalyst. Remember, this is also a syn addition. And what are you adding? Just 2 hydrogens. So if both hydrogens get added to, let's say, the bottom face, if the H's get added below, what happens to those methyls? They get pushed up to the other face. So the methyls are just kind of hanging out. They just do the opposite of whatever else comes in. Versus, what if both H's get added to the top face, methyls get pushed down? Is that different? No, that's going to be the same thing, but if you want to draw it, you can, but cross it out. Do not include it. That is not a different structure. That's it. Those are the reactions of the alkenes. Is there more than this? I mean, in terms of predicting the product, no. But should you know the mechanisms? Of course. But in this, we just wanted to kind of cover all the reactions together so you have a pretty good grasp of it all.